In this video, we are going to go over buffers. So a buffer is a solution that resists changes in pH when small amounts of acid or base are added. This is how acid-base homeostasis works to prevent acidosis and alkalosis. When the blood plasma pH is outside the physiological pH range of 7.35 to 7.45 range, cells can't function properly. Yet hydronium and hydroxide ions are absorbed and released continually into our bloodstream from the foods we eat and produced from cells during normal metabolism. So how then is it possible to prevent fluctuations in blood plasma? Blood, as well as other aqueous systems in nature, contain buffers. A buffer component, the components of a buffer system are a weak acid and its conjugate base, in similar concentrations or within a tenfold difference. The pH range is maintained by the buffer, depends on the identity of the weak acid that's in the buffer. So these are some common buffers. The acetic acid and acetate buffer, you can see the weak acid is acetic acid, its conjugate base is acetate, and the function is a common laboratory buffer. There's carbonic acid and hydrogen carbonate buffer, and that's an extracellular buffer. And then dihydrogen phosphate and hydrogen phosphate, it's an intracellular buffer and also a common laboratory buffer. And each of these have a specific pH range that they can maintain. So for practice, which of the following aqueous solutions is a buffer? Remember, for a buffer, we need weak acid and its conjugate base. HNO3 and NaO3 doesn't work. That is a strong acid. H2CO3 and HCO3, that is a base, and we don't use that. NaCl and KCl, those are salts. Citric acid and sodium citrate. Citric acid is a weak acid, and the conjugate base of citric acid is sodium citrate. So this is a buffer. KOH and H2O. KOH is a strong base, and H2O is not even a conjugate acid or base, or conjugate acid of the base. The buffer equilibrium. So buffers have a weak acid in water goes to hydronium ion plus the conjugate base. Adding H3O plus, so if you add acid, you increase the rate of the reverse reaction, producing more weak acid and water and a shift to the left, according to Le Chatelier's principle. The conjugate base reacts with the added hydronium ions to make more of the weak acid and the H2O in the reverse reaction, therefore decreasing the amount of conjugate base in solution. The concentration of H3O plus changes minimally and the pH remains relatively constant, because when you add it, the conjugate base starts reacting with it and it doesn't, and it starts breaking down. So the change in it, so the overall change is minimal. Adding hydroxide decreases the hydronium ion concentration, which slows the rate of the reverse reaction, producing more H3O plus and conjugate base and a shift to the right. So if we increase hydroxide concentration, we decrease hydronium ion concentration. Again, the hydronium ion concentration only changes a little, resulting in a relatively constant pH. Because remember, the point of a buffer is to maintain your pH equilibrium and make it so that your pH doesn't change too much. The acetic acid acetate ion buffer, the buffer range of this buffer system is 3.8 to 5.8. You have acetic acid, which is a weak acid, plus water goes to hydronium ion and acetate ion. If you add hydronium ions, it goes to the left. If you remove hydronium ions, so you're decreasing H3O plus, or if you add hydroxide or add a base, you shift to the right. And of course, and remember, this is all according to Le Chatelier's principle. The buffer capacity is the amount of acid or base that can be added to a buffer without a change in pH occurring. The greater the concentration of the buffer components, the weak acid and conjugate base, the greater the buffer capacity. Adding an amount of base or acid in excess of the buffer capacity will cause a change in pH. So your buffer capacity, you can only keep your pH in a certain range up until the buffer capacity. If you exceed that capacity, then your buffer is no longer workable and doesn't work anymore, and then now you get the drastic changes for your pH. So in summary, a buffer contains approximately equal concentrations of a weak acid and its conjugate base, thus resisting changes in pH when a small amount of acid or base is added. It has to be less than the buffering capacity. The components of a buffer, a weak acid and its conjugate base, are in equilibrium in aqueous solutions. A buffer resists change in pH because the equilibrium shifts in response to either addition or removal of hydronium ions. So adding an acid is an addition of hydronium ions. Removal of hydronium ions is adding base. And this maintains the concentration of the hydronium ions. The addition of hydroxide ions is equivalent to the removal of H3O+. The buffer capacity is the amount of acid or base that can be added to a buffer without a change in pH occurring.